In electron energy loss spectroscopy, a material is exposed to a beam of electrons with a known, narrow range of kinetic energies. Some of the electrons will undergo inelastic scattering, which means that they lose energy and have their paths slightly and randomly deflected. The amount of energy loss can be measured via an electron spectrometer and interpreted in terms of what caused the energy loss. Inelastic interactions include phonon excitations, inter- and intraband transitions, plasmon excitations, inner shell ionizations, and Cherenkov radiation. The inner shell ionizations are particularly useful for detecting the elemental components of a material. For example, one might find that a larger than expected number of electrons comes through the material with 285 electron volts less energy than they had when they entered the material. This is approximately the amount of energy needed to remove an inner shell electron from a carbon atom, which can be taken as evidence that there is a significant amount of carbon present in the sample. With some care, and looking at a wide range of energy losses, one can determine the types of atoms, and the numbers of atoms of each type being struck by the beam. The scattering angle can also be measured, giving information about the dispersion relation of whatever material excitation caused the inelastic scattering. History. The technique was developed by James Hillier and R. F. Baker in the mid-1940s but was not widely used over the next 50 years, only becoming more widespread in research in the 1990s due to advances in microscope instrumentation and vacuum technology. With modern instrumentation becoming widely available in laboratories worldwide, the technical and scientific developments from the mid-1990s have been rapid. The technique is able to take advantage of modern aberration-corrected probe-forming systems to attain spatial resolutions down to 0.1 nanometers. While with a monochromated electron source or careful deconvolution, the energy resolution can be 0.1 electron volts or better. This has enabled detailed measurements of the atomic and electronic properties of single columns of atoms, and in a few cases, of single atoms. EELS and EDX. EELS is spoken of as being complementary to energy-dispersive X-ray spectroscopy, which is another common spectroscopy technique available on many electron microscopes. EDX excels at identifying the atomic composition of a material, is quite easy to use, and is particularly sensitive to heavier elements. EELS has historically been a more difficult technique but is in principle capable of measuring atomic composition, chemical bonding, valence and conduction band electronic properties, surface properties, and element-specific pair-distance distribution functions. EELS tends to work best at relatively low atomic numbers, where the excitation edges tend to be sharp, well-defined, and at experimentally accessible energy losses. EELS is perhaps best developed for the elements ranging from carbon through the 3D transition metals. For carbon, an experienced spectroscopist can tell at a glance the differences among diamond, graphite, amorphous carbon, and mineral carbon. The spectra of 3D transition metals can be analyzed to identify the oxidation states of the atoms. Cu, for instance, has a different so-called white line intensity ratio than Cu. This ability to fingerprint different forms of the same element is a strong advantage of EELS over EDX. The difference is mainly due to the difference in energy resolution between the two techniques. Variants. There are several basic flavors of EELS, primarily classified by the geometry and by the kinetic energy of the incident electrons. Probably the most common today is transmission EELS, in which the kinetic energies are typically 100 to 300 keV and the incident electrons pass entirely through the material sample. Usually this occurs in a transmission electron microscope, although some dedicated systems exist which enable extreme resolution in terms of energy and momentum transfer at the expense of spatial resolution. Other flavors include reflection EELS, typically at 10 to 30 keV, and aloof EELS, Within transmission EELS, the technique is further subdivided into valence EELS and the inner shell ionization EELS. The dividing line between the two, while somewhat ill-defined, is in the vicinity of 50 electron volts energy loss. Thickness measurements. EELS allows quick and reliable measurement of local thickness in transmission electron microscopy. The most efficient procedure is the following. Measure the energy loss spectrum in the energy range about -5 to 200 electron volts. Such measurement is quick and thus can be applied to materials normally unstable under electron beam. Analyze the spectrum. Extract zero-loss peak using standard routines. Calculate integrals under the ZLP and under the whole spectrum. The thickness T is calculated as MFP** lane. Here MFP is the mean free path of electron inelastic scattering, which has recently been tabulated for most elemental solids and oxides. The spatial resolution of this procedure is limited by the plasmon localization and is about 1 nanometer, meaning that spatial thickness maps can be measured in scanning transmission electron microscopy with ~1 nanometer resolution. Pressure measurements. The intensity and position of low-energy EELS peaks are affected by pressure. This fact allows mapping local pressure with ~1 nanometer spatial resolution. Peak shift method is reliable and straightforward. The peak position is calibrated by independent measurement using a diamond anvil cell. However, the spectral resolution of most EELS spectrometers is often too crude for the small pressure-induced shifts. Therefore, the sensitivity and accuracy of this method is relatively poor. Nevertheless, pressures as small as 0.2 gigapascals inside helium bubbles in aluminum have been measured. Peak intensity method relies on pressure-induced change in the intensity of dipole forbidden transitions. Because this intensity is zero for zero pressure, the method is relatively sensitive and accurate. However, it requires existence of allowed and forbidden transitions of similar energies and thus is only applicable to specific systems, e.g., Xe bubbles in aluminum. EELS in confocal geometry. Scanning confocal electron energy loss microscopy is a new analytical microscopy tool that enables a double-corrected transmission electron microscope to achieve sub-10 nanometers depth resolution in-depth sectioning imaging of nanomaterials. It was previously termed as energy-filtered scanning confocal electron microscopy due to the lack to full spectrum acquisition capability. SCELM takes advantages of the newly developed chromatic aberration corrector, which allows electrons of more than 100 electron volts of energy spread to be focused to roughly the same focal plane. It has been demonstrated that a simultaneous acquisition of the zero-loss, low-loss, and core loss signals up to 400 electron volts in the confocal geometry with depth discrimination capability